Chemistry section 2.2 part 7. The focus for today's lesson is going to be on naming and formula of ionic compounds. Okay, so we are moving on to naming and formulas of compounds. So this should all be review from Science 9. However, we're going to go through it as if you have kind of a vague idea of it, but you don't really remember a lot. Okay? So ionic compounds are made up of positive and negative ions, so metals and nonmetals. So all of the positive and negative ions organize in a pattern. So this is again where it's not just one sodium and one chlorine together, and that's sodium chloride. It's that it forms kind of a structure, kind of like a crystal lattice is an example of one of these structures. So negative and positives attract. So remember, opposites attract. Negative and negative repel. Positive and positive repel. So if you have the same charge, they're going to repel one another. Ionic compounds form from the inside out as solid crystals. So they start on the inside, they expand out. Ionic compounds are like solid stacks of brick. So a salt shaker contains thousands and thousands of small pieces of NaCl, which have formed together in a crystal lattice structure. Covalent molecules, on the other hand, share electrons. There is generally no order of the formation of covalent molecules. So think, for example, like a water molecule. There can be one, and then there can be many of them. They're not in a lattice structure. They're just kind of all together forming clumps of either solids, slightly more spaced out liquids so they can flow, or gases if they're really spread out. So think of like our diatomic molecules, for example. Covalent molecules are like a play pit full of plastic balls. So if you've ever went to one of these as a kid, there's an individual ball that represents one covalent molecule, and then together it's still a bunch of those covalent molecules. So one molecule is H2O, however, together you have a bunch of H2O molecules which make up water. It's good to know that covalent molecules, again, the sharing of electron occurs between non-metals. So there's no metals involved. So chemical name and formula of ionic compounds. Ionic compounds are composed of positive ions and negative ions, metals and nonmetals. The name of an ionic compound is a positive ion and then the negative ion. So sodium chloride. Sodium is the metal. Chlorine, which we changed to chloride, is the nonmetal. For example, an ionic compound forms between magnesium and oxygen. The positive ion is the first part of the name, magnesium. We never change anything about the first element. The negative ion, though, forms the second part of the ending. So in this case, it's oxygen, but we have to change the ending here. Oxygen's kind of a unique one because of the YG in it. So we change the oxygen to IDE. IDE. So magnesium oxide, nitrogen would be nitride, sulfide, phosphide, etc. So always make sure you're changing the ending to IDE. Ionic formulas are based on the ions of the atoms involved. Remember the naming principles above. So for example, what is the name of Ca3N2? So first we're going to look at the elements without the numbers. So Ca, if we look on the periodic table, is the positive ion. This is calcium. So remember positive ion first. This is our metal. N is our non-metal, negative ion. This is nitrogen. But it's not calcium nitrogen. We need to change and add the ending IDE. So this ogen becomes ide. So calcium nitride. Okay, really make sure you understand this. It's super important. Okay, so let's practice here. I will do one and then you can go through and practice the rest. So Ca on our periodic table represents calcium And then Cl is chloride. Sorry, it's chlorine on the periodic table. So we're going to put these together, change the ending to calcium chloride. Okay, really important, change the ending. So go through, pause here if you need to. This is also in your notes, but you should be able to complete these examples. I will have answers posted after. 4 formulas for ionic compounds, and again, this is ionic. In an ionic compound, the positive charges balance out the negative charges. So that means that it should equal out to 0 in the end. The ratio of positive to negative charges gives the proper formula. The ratio is always written in reduced form. So just like in math, if you have a ratio of 2 to 2, we reduce that to 1 to 1. Okay, this is kind of like if I was to go back and look at, so as I was kind of saying before, the crystal lattice structure that an ionic compound forms isn't just made up of one Na and one Cl atom. It's something like, say, I don't know, Na, we have 100 of them, and then Cl, we also have 100 of them. So it's a 1-to-1 ratio, basically. So we reduce this down to NaCl. And we don't write ones, but essentially what we've done is divide this by 100 and divide this by 100. Okay, so back to this slide. I'm going to walk you through the examples here in words, and then I'll write them out separately on the second sheet so that you have a better idea of what we're doing. So magnesium phosphide. Magnesium has a 2+ charge. Based off of our periodic table, it has 2 electrons that it can give away. Phosphorus has a 3- charge, and the lowest common multiple, meaning what is basically 2 times 3, is 6. So in order for the charges to balance out, we need 3 of the magnesium 2+, giving us an overall 6+ charge, and we need 2 of the phosphorus -3 charges, which would be -6. So overall, that charge is 0. So Mg3, so notice that this 3 represents the little subscript 3, and this 2 represents the little subscript 2 here. So it's saying that we need 3 magnesium for every 2 phosphorus. Going over calcium oxide quickly now. Calcium is +2 on the periodic table. Oxygen is 2- charge. This is already in a 1-to-1 ratio. It's already balanced. 2+ plus -2 is equal to 0. So we have 1 Ca2+ ion for every 1 O2- ion. So if you were to do the crisscross method from last year, you would end up with Ca2O2, but this isn't finished, it's not simplified, it needs to be reduced to CaO, so dividing both by 2 essentially. Okay, so actually breaking this down into steps. Magnesium has a 2+ charge, and phosphide, which is phosphorus, has a 3- charge. We want to think about the lowest common multiple, which is 6, so 2 times 3. So we want this to be a 6+ charge, and we want this to be a 6- charge. So we need 3 of these. So Mg2+, that would be a 4+ charge. Mg2+ again would give us overall 6. So we have 3 of them. Phosphorus is already 3-, so we need another 3. So overall, that is a 6- charge. So this means that we have Mg3 for 3 of them, P2. For calcium oxide, we have symbol Ca, charge is 2 plus, and oxygen is O2 minus. So this overall is already a 2 plus charge, and this overall is a 2 minus charge. So that's already balanced. It already equals out to 0, which is neutral. So we have one of each molecule. So we have, CaO. We don't write ones in our chemical formula, so CaO is the final chemical formula for this one. If you wanted to do the crisscross method for either of these, and again, I do not recommend doing the crisscross method unless you understand the balanced charges. So for magnesium, you take the charge from the upper position and cross it to below, like this. So it becomes from the superscript to the subscript, Mg3P2. Again, same final formula. The difference is with this one, you can commonly make a mistake, where with the balanced charges, it is much harder to do or to make a mistake. For example, if you were to just take Ca2 plus O2 minus and use the crisscross shortcut, you'd end up with Ca2O2. This is incorrect. It's not reduced. This would be wrong. So you need to then divide this by 2 in order to reduce it to get CaO in the final form. Okay? So again, this is a shortcut. It's not meant to replace balanced charges. Balanced charges helps you to understand how many of each element are needed to balance out the charges of each other. So that was kind of what I just showed you. It's important if you are doing the crisscross method that you do remember to always reduce. Okay, so if you have element A, which has a 2 plus charge, element B, which has a 2 minus charge, you end up with A2B2. That can be reduced, you reduce it. If you had something like A4B2, you would reduce this down to A2B. Okay, so always, always, always reduce. Okay, next set of examples here, practice writing formulas for the following. I'll do the first one and then pause here, and I have the answers on the next slide. So silver chloride, we've got our ions, Eg for silver, which has a 1 plus charge, Cl, which has a 1 minus charge. The formula for this, it's already in a 1-to-1 ratio. AgCl is the final formula for this. Okay? So here are the answers. This is done really simplified. If you need to go review the balancing charges, go back to my previous examples. But these are examples. The diagram at the bottom is a puzzle piece visual model to show you that you need these prongs to fit together like a puzzle piece. So if I count, I have 1, 2, 3 prongs on each nitrogen. And so total for nitrogen, I have 6 prongs. Now, if I look at the barium, I have 1, 2 on each. There's 3 of them. There's 6. So that's representing the positive 6. The prongs on the nitrogen are representing the negative 6. That balances out to equal 0. These 3 green things represent this 3 right here, and the 2 red nitrogen visuals represent the 2 here. Okay, so it's a puzzle piece model that some teachers would use in grade 9 to show this. Okay, so looking at this slide, for example, we're going to focus on the element iron. So on our periodic table, if we look at it, it has a 3 plus and a 2 plus. This is from Science 9, and it's referred to as multivalent metal, meaning it has multiple charges. So do you see any trends here? Take a minute, pause if you need to. But what you should notice is that this is referring to Fe3+. So this 3+ is represented by this Roman numeral, and this represents this Roman numeral. So the brackets tell us which charge for the multivalent metal we are going to use. So Fe3+, O2- are our ions here, and then Fe2+, O2- for our second example there. So then if you were to write the formulas of these multivalent metals using the balanced charge method, for example, or crisscross, either will work, we end up with the formula for iron 3 oxide is this one, and iron 2 oxide is this one. So again, those brackets tell us which charge we're using. So some transition metals are multivalent, meaning they have more than one ion form. On the periodic table, the most common form of the ion is listed on top. So for example, for the magnesium, 2+ is the most common form. In the name of the compound, so when we're naming, we use Roman numerals following the positive ion to indicate which ion was used. So for example, what is the formula of manganese 3 sulfide? The 3 tells us that we need to use the 3+ ion for manganese, and sulfur, based on sulfide, only has one charge, and that is 2- based on the periodic table. So again, if we consider the lowest common multiple between 3 and 2, that is 6, meaning that we need 2 manganese 3+ to give us that 6+ charge, and we'd need 3 sulfur ions to give us the 6- charge in order to make sure those are balanced. So you end up with the 2 representing this and the 3 representing this in the manganese 2 sulfide formula. So again, another example, TiF4. So if we look at the periodic table, titanium has 2 possible charges, where fluorine has a -1 charge. So we're going to work with what we know here. Each fluorine ion has a -1 charge, and we're told we have 4 of them. So total, this would be a 4- charge. In order to get that 4+ charge, and we're told we only have 1 titanium, this titanium molecule must have a 4+ charge, because if it was the 3+ charge, it wouldn't balance properly. So what this tells us is we have 1 titanium ion for every 4 fluoride ions. So therefore, 4+ is being used here. So the name of this particular molecule would be titanium 4, which is IV, fluoride. So when you're going from formula to name, with multivalents in particular, you're essentially working backwards. You always want to work with the non-metal first because the charge, there's only one option for it. And then you want to think, how many of them do I have? So if there's 4 of them, they each have 1- charge, meaning that there's a -4 charge overall. In order to balance that charge, our 1 titanium in this example, could have been 2 for something else, would need to have a 4+ charge to balance. Okay, so try the other 2 examples on this sheet. And then I will, so pause, and then I will show you the answers on the next slide. Oh, also just a reminder of your Roman numerals. You should know these. For the most part, you're only ever going to go as far as, I think 4+ is as high as we ever deal with. There are some examples of 5+. So basically know 1 to 5 really well. Okay, here are your answers. So lead to iodide, Pb2+ and I-. So working with the iodine, we would need 2 of those to balance out that 2+ charge. CO2O3, we work based off of the oxygen, which has a 2- charge. So the lowest common multiple between these is 6. So for our oxygen, we have 3 of them. So O2-, 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 giving us an overall 6- charge. And each of our cobalts has a 3+ charge, and we have 2 of them. So that will give us our 6+ value. So this tells us that we are working with cobalt-3 oxide. So off to the side, I've just written out that based on the nonmetal for cobalt-2O3, or CO2O3, we know for sure that there are 3 oxygens, and each have a 2- charge because that's the only possible charge for oxygen. So total, that's a 6- charge, which we've got here. So to balance that, we need a 6+ charge. The 2 tells us here that we have 2 cobalts, so that 6+ charge must be distributed between 2 cobalts. So we can think of it as either what is 6 divided by 2, which is 3, or you can kind of trial and error it, and you know that 3 + 3 is 6. So each one of these will have a 3+ charge on them. And that's how we determine that it is cobalt 3+, which is what this tells us. So cobalt-3 oxide. A bit more practice for you to work through. The first example is completed for you, so you can fill in the remainder of this table. I will post the answers for you. More practice again. So next we'll be looking at polyatomic ions. So splitting the word up, and this again should be a review from last year. Poly means many, atom means atoms, and then ion means it's charged. So some ions called polyatomic ions are made up of several atoms joined together with covalent bonds. These are listed on the table at the bottom of the slide here. You'll notice that all of the polyatomics have multiple kind of capital letters in them. So this is kind of a hint to know that you're dealing with them. So the polyatomic ion is a positive or negative charge, not the individual atoms. So the whole thing together, you can't separate the polyatomic ion. It is one package deal. It stays together. It does not ever split up. So don't try and split it up. NO2, for example, here, it's a covalently bonded ion. It does not split up. The N will not separate from the O2. That is its state. That is how it stays. So that's the same with all of these. Majority of them are negative ions, so they act like nonmetals, with the exception of ammonium, which is NH4+. So this is the only positive polyatomic ion. The rest are all negative. So again, make sure you don't ever split them up. Some ones to watch out for: the sulfates, sulfites, phosphate, phosphite. These sound very similar to phosphide and sulfide, which is just P and S. So please be aware of these endings here. 8 usually refers to O4, and ite refers to O3. So if you read them, you'll see some of the similarities between some of the names, okay? You're not required to memorize this table. You will be provided with it. Okay, a few more examples to go through here. I'll go through the ones in the top in gray, and then you can do the 2 at the bottom, and I will have the answer key after this, so you can just pause in between. Okay, so sodium sulfate. So we're dealing with Na plus, and sulfate, if we look at the polyatomic ion list, again, important to look at that 8 at the end, is SO4, and then the charge on that is 2 minus. Working through this, we have SO4, 2 minus, which would have an overall 2 minus charge. So that means we have to have a 2 plus charge to balance that out. So Na has a 1 plus charge, so that means we need 2 of them to balance that charge out. So you're going to end up with Na2SO4. Okay, so again, that 2 tells us that we have 2 Na ions for every 1 SO4 polyatomic ions. Notice that again, I have kept SO4 as SO4. It exists as one thing. We do not split it up. Okay, next, what is the name of the compound KClO? So K is our metal, and this is potassium. And potassium has a 1 plus charge. And then ClO is our hypochlorite. It also has a minus charge. Because potassium is not multivalent, we can just go in and name it right away. We don't have to worry about figuring out the charge or anything like that. So there is no Roman numerals when it is not a multivalent, so a transition metal. Okay, so this is potassium hypochlorite. Okay, so again, that hypochlorite is just named off of the back of the periodic table. There's a chart for polyatomics. You are not expected to memorize those polyatomic names. Okay, so pause here, try these last 2 examples. I will put up the answer key. Okay, so here are the answers to the 2 practice questions. So barium perchlorate, it's important that because we have 2 of these for the perchlorate, that we have those brackets surrounding the ClO4. This is because that 2 applies to everything within the brackets. So it means that we have 2 Cl atoms and then actually 8 oxygen. So if you were to actually count out the individual atoms of this polyatomic, that's what it would look like. So that 2 needs to be bracketed around the entire thing. So make sure you've got those brackets. We don't need a bracket if it's just one of them. Careful with that ending again. Okay, some more practice for you to work through. Again, there will be an answer key posted. And that is going to be the end of this video section.